In this section, 11.4, we're finally going to be talking about a probability. When we say probability, what it is a computation, or what we're computing is the likelihood that an event will happen. In the table below, here's an example. This table represents the hours of sleep Americans get on a typical night. So the total number of Americans, and that's in millions, is 300 million. So this particular survey deals with 300 million Americans. Now in the first column, we have the hours of sleep they get on a typical night. So if you look at the first row, 4 or less hours of sleep, about 12 million Americans get 4 or less hours of sleep. We look at 5 hours, 27 million, and so on. So if we look down to 6 hours of sleep per night, 75 million Americans get 6 hours of sleep per night. So the probability of an American getting 6 hours of sleep on a typical night is a fraction, where the denominator or bottom of the fraction represents the total. So the total here is the 300. So out of those 300 million Americans, the numerator or the top is the particular event we're looking at. So the event we're looking at is 6 hours of sleep per night, which is 75. So 75 out of the 300 million get 6 hours of sleep per night. Whenever we write our probabilities, it'll be a fraction, and we reduce fractions. So 75 over 300 reduces to 1/4. However, we can also write the probability as a decimal. In this case, it would be 0.25, or we can write the probability as a percent. In this case, it's 25%. So what that means is if you randomly choose one American out of the 300 million, the chance that you will pick somebody, or the probability that you would pick somebody that gets 6 hours of sleep per night, is 75 over 100, or about 25%. There are two types of probabilities. The bulk of this course is going to be based on theoretical probability, but there's also empirical probability. Basically, empirical probability means that you base your probability on an actual experiment where you observe occurrences. But theoretical probability is a little bit different. In theoretical probability, we don't conduct experiments or do anything like that. What we assume is that all of our outcomes have an equal probability of occurring. So we'll look at an example about what that means in just a second. But first of all, I want to go over some notation that you might see. If you see a capital S, that stands for a sample space, which is the set of all possible outcomes. Going back to our table, our sample space is all the possible things that could happen. So in our case, this would be the 300. So it's like a total. The event, our event is a subset of our sample space. But it's a particular outcome that we're looking at. In our case, we're looking at the 75. That was our event. If you see a capital P, that usually stands for probability. So let's review this notation. Let's say that you toss a coin twice, and you want to find the probability that you get heads on both tosses. Here, we're dealing with theoretical probability, so we're not actually going to toss a coin and see what happens. What we're going to do is assume that we have an equal probability that the coin will land heads up or the coin will land tails up. Again, that's theoretical probability. We assume the outcomes have an equal probability of happening. So the event we're looking for is tossing the coin twice and getting heads on both tosses. So that's our event, which is usually a capital E. To make things easier, I'm going to do an abbreviation. I'm going to let capital H be heads. So capital H, if I toss the coin and it lands heads up, that's a capital H. I'm going to let capital T be tails. So my event is going to be 2 tosses. 1, 2. The first toss, I'm looking for heads on both, so heads. The second toss would also be heads. So I could just look at this as an abbreviation of getting heads, heads. Let's look at our sample space. So the sample space is all the possible outcomes when you toss a coin twice. The sample space, and I'll use that capital S, is a set. So this set is, and whenever we talk about sets, we use these curly braces. These are set braces. So the set of all possible outcomes would be heads on the first toss, heads on the second toss. Or I could get heads on first toss, tails on second toss. What if I get tails on the first toss and then second toss is heads? Or I could get tails on both. So these are all the possible things that can happen when I toss that coin twice. Now, when you're figuring out your sample space, you can also use a tree diagram if you wish, similar to what we did in 11.1. Let's say that you look at your first toss. It's possible that on your first toss you could get heads, or your first toss you could get tails. Well, let's say you got heads on your first toss, then your second toss possibility would be heads or tails. Let's say you got tails, then when you toss it again, you could get heads or tails. So if you look down on these branches, we have heads, 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 tails, tail, head, tail, tail, which is our sample space that I computed for you. Let's look at the event. The event we're looking for, and I'll use a capital E for this event, the event we're looking for is heads on both toss. So I have to, and it's a set, write down all the possible outcomes that give me heads on both tosses. And there's only one. It would be heads on first, heads on second. Now, let's go to the probabilities. The probability of getting heads on both tosses, well, you may see it written this way. P for probability, parentheses would be the event, and that would be heads on both tosses. So that's the particular event we're looking for. But I can also abbreviate this as the probability parentheses heads first, heads second toss. Probabilities, we always write it as a fraction. And then if we need to write it as a decimal or a percent, we can convert it later. So the probability is always a fraction. In the denominator, in the bottom, is all the possible things that can happen, which would be how many things are in your sample space. Now there's 4 outcomes in my sample space, so there's 4 possible things that can happen. In the numerator, in the top, we're going to put all the ways our event can happen. When you look at our event, there's only one thing there. There's only one way that you can get heads on both tosses. So the probability that you flip a coin or toss a coin twice and you get heads on both tosses is 1/4. In this example, what I wanted to do is just let you become familiar with different notation that you're going to see. But when we are computing, and this is for theoretical probability, not empirical, sorry. When we are computing theoretical probability, here the probability that an event will happen is going to be the number of event outcomes. So the number of ways the event can happen over the number of possible outcomes, which would be this n of E, n of S. So what does that n stand for? So in set notation, this n is this number. So it's the number of ways our event can happen. So the n is the number of ways the number of possible outcomes, or the number of things in your sample space. So just be aware that when we're figuring out a probability, it's always going to be between 0 and 1. It can equal 0. It can equal 1. It cannot be greater than 1. It cannot be a negative number. So if you're figuring out a single probability and you get a number greater than 1 or a negative number, double check your math. Now, if we were writing the probability as a percent, then it would be between 0% and then 1 is 100%. If you get a probability that's a negative percent or a percent over 100%, that's not possible. Now, I'm assuming that you guys are all familiar with a regular six-sided die. So here's a example of a pair of die. So when you have, it's like mouse mice. When you have a single die, it's not dice, it's die. When you have more than one, that's when it's plural, so it's dice. So these are a pair of dice. It's a standard six-sided, which means that the numbers go from 1 to 6. In this example, I'm going to use all that notation that we talked about on the previous page, and then I'm going to kind of not use that notation anymore. I'm only using it so you're familiar with it in case it comes up in your MyLab or in your textbook. And then I'll switch to not even using that S, E, and P. Maybe I'll use it once in a while, but not so much. Example 1, we have a six-sided die, and we're going to roll it once. So we want to find the probability of rolling in part A, a 2, in part B, a number less than 3. So let's look at the solution. Well, the first thing I want to do is figure out my sample space. Your sample space would be all possible outcomes, and in this case, it's going to be the set of 1, 2, 3, 4, 5, 6. So those are all the possible numbers I can roll when I roll that standard six-sided die. So the number of things or items in my sample space is 6. The event that I have for part A is rolling a 2. So how many ways can I roll a 2? There's only one. So in my event, the only way I can roll a 2 is by rolling a 2, which means there's only one thing in that set. So the probability of rolling a 2 is going to be a fraction where the denominator is everything that could happen, which would be the number of things in your sample space, over your event, which is 1/6. And of course that makes sense, right? 6 possibilities, only one of those is a 2. Let's try another one. For part B, our event is going to be rolling a number less than 3. So you have to be careful because less than and less than or equal to are two different things. Excuse me. So this is less than. Sample space is still the same. So let's look at our event. 1 is less than 3. 2 is less than 3. 3 is not. So there's only two numbers that I can roll for this event, which means there's two things in my event. So the probability of rolling a number less than 3 is a fraction. Denominator is everything that can happen. Top is your event. So 2/6. Out of the 6 possibilities, there's 2 ways to get a number less than 3. I would not leave my answer that way because I can reduce this to 1/3. So don't forget to reduce your fractions. So now I'm going to put a hold on all that notation. Notice that we did dice, we flipped coins. Now I'm looking at a deck of cards. Oftentimes when we look at probabilities, It tends to address issues of gambling. That comes up a lot if you go to Vegas and you gamble. And it actually turns out that when you look at all the games in Vegas or any gambling type of game with cards or dice or roulette wheel and so on, it turns out that craps, dice, gives you the best chance of winning. This is a standard 52 card deck if you're not familiar with a deck of cards. There's 4 suits: spades, hearts, diamonds, clubs. Half the deck is black, half the deck is red. The ace, we're going to consider an ace as 1. So if you look at these cards, we go from ace, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And then once we reach 10, we look at our picture cards, which would be a jack, a queen, and a king. So for each suit, this is the suit of spades, and there's 13 spades. 10 of those are number cards. 3 of them are the picture cards, jack, queen, king. And then that would be the same for the hearts, the diamonds, and the club. In example 2, you're dealt 1 card from a standard 52 card deck. Find the probability of being dealt part A, an ace, part B, a red card, part C, a red king, and D, a picture card. So A, I'm looking at the probability that I'll get an ace, and I'm not going to use any of that notation. I'm going to start out with my fraction. The bottom is all the possible cards I could get when I'm dealt 1 card, and there's 52 cards in that deck, so 52 possibilities. Of those 52 cards, how many of those are aces? And there are 4 aces. So again, reduce. This reduces to 1 over 13. Let's look at B. A red card. Well, out of the 52 cards, half of them are red. If you count the red cards, there's 26, which gives us the 1/2. Makes sense because half the deck is red. Let's look at C. A red king. Again, it's a probability, 52 outcomes. How many of those are red kings? Well, there's a king of hearts and there's a king of diamonds. So there's 2 red kings in the deck of 52, which gives me a probability of 1 over 26. I'm leaving these all as fractions, and my lab will typically leave things as fractions. But remember, you can also write this as decimals. You can write these as percents as well. So just be aware that on my lab, you may be asked to write something as a decimal or a percent, but usually it's going to be a reduced fraction. D is a picture card. So again, I'm finding a probability. It's a fraction, 52 possibilities. How many of those cards are picture cards? Well, there's 3 picture cards for each suit, and there's 4 suits, so that should be 12. And then when I reduce it, it looks like it's divisible by 4 on the top and bottom. I get 3 over 13. Now, I don't know if you had a biology class or if you've looked at genetics at all. So every person gets a set of genes from both parents. So they usually come in pairs. Eye color, you'll get 1 gene from your mother, 1 gene from your father. If it's a dominant trait, it'll show up. So you'll physically see that on the person's body. If it's a recessive trait, you need to get the gene from both parents for it to show up on your body. I don't know if you know the difference between an attached earlobe and an unattached earlobe, but when you look at your earlobe, if it kind of hangs down, that's an unattached earlobe. If it doesn't, then that's an attached earlobe. Unattached earlobes are dominant traits, so you only need the gene for unattached earlobe from one parent for you to have unattached earlobe, which is what most people have. About roughly 25% of the population has attached earlobes. So to have an attached earlobe, nothing hangs down, then you would have had to have that gene from both parents for it to show up. So typically when we're doing genetics, we'll let the capital or the big letter. So we use letters to stand for different genes. A big letter or uppercase letter means dominant, lowercase or small letter means recessive. In example 3, each person is going to carry 2 genes that are related to the absence or the presence of cystic fibrosis. So this is where genetics is really important. It's in looking at diseases or genetic defects that could happen when we pair 2 people together. So most Americans carry 2 normal genes. 1 in 25 Americans carry 1 normal gene and 1 defective gene. So the normal gene is going to be a dominant gene, and that's going to be our capital C. The defective gene, which would be the presence of cystic fibrosis, would be the little c. So it's recessive. So in order to have 1 normal and 1 defective, you would have to have a big C, little c combination. That means you're a carrier, but you're not sick, so you don't have symptoms of the disease. Now, if you have 2 big C's, that means you're not a carrier. You don't have cystic fibrosis. If you have 2 little c's, that means you are actually sick from cystic fibrosis. So I already talked about those highlighted blues that we don't denote dominant traits with a capital letter, recessive traits with lowercase letter. 2 recessive genes are needed for the trait to appear. 1 dominant gene is needed for that trait to appear. So the first thing we're going to do is we're going to fill in our genetic chart. And let's say that we have these 2 parents. Again, the parents have 1 big C, 1 little c. So that means they're carriers, but they're not sick. So let's see the possibility of their child. So let's say the first parent passes on the big C and the second parent passes on the big C. So that combination would be big C, big C. It's like a multiplication chart. So let's say first parent is big C, second parent gives little c. That combination would be big C, little c. What if the first parent passes on little c and then big C from the second parent? So we have little c, big C. And then the last combination would be that each parent passes on little c. So little c, little c. So those are the 4 possibilities. That's our sample space for a child that has these 2 parents. Part 2, what is the probability that these parents will have a child that is a carrier, but who is not actually sick? So carrier, not sick, would be a big C, little c, and the order doesn't matter. It could be little c, big C. So since it's a probability, it's a fraction, where the denominator is all the possible things that could happen. So it would be those 4 outcomes that we see in the table. Of those 4 outcomes, how many of those are big C, little c? And that would be 2 of them. So 2 out of 4, or 1/2. So think about this. If parents are carriers, they have a 50% probability that their child will also be a carrier. Part 3, what is the probability that these parents will have a child who's actually sick? So a child that is actually sick, that would be 2 little c's. And if you look at the table, there's only one way that can happen. So again, we're looking at a probability, it's a fraction. In the bottom, there's the 4 possible outcomes. In the numerator, this particular event, there's only one way that this can happen. So there's a 4th chance, or 25% chance, that carriers can have a child that actually has cystic fibrosis. So probability, so not just for gambling. Now we want to actually talk about empirical probability. The bulk of the course is theoretical probability, but we would like to talk about empirical probability. And that would be based on observed events, which means you actually do conduct an experiment and your results are based on those experiments, or your probabilities are based on the experiment. So the probability that an event will happen with empirical probability is the observed number of times the event occurs over the total number of observed occurrences, which is probably just a bunch of words at this point. Let's look at an example. Example 4, you conduct an experiment and toss a coin 100 times. You observe that the coin lands heads up 44 times. So part 1. Based on your observations, if you toss this coin one time, what is the probability that it will land heads up? So it's a probability. We're looking at a fraction. The event is landing heads up. So this event heads up, we found that that was 44 times in our experiment. We tossed the coin a total of 100 times. So the total number of observed occurrences would be 100. Tossed it 100 times, 44 times heads up. And that's it. So reduce it to 11 over 25. Or remember, we can also write this as 44%, or we can write it as 0.44. Just make sure that you're reading the MyLab exercises correctly. Part 2. If a coin is fair, then there's an equal probability of getting heads or tails on a toss. Is your coin fair? And the answer is no, it's not fair. It's not a fair coin because if it were fair, when you toss it 100 times, you should have heads 50 times and tails 50 times. And that's typical of a coin. And in fact, any object, if you toss it in the air and you let it fall, most times it lands heavy side down, light side up. I don't know if you play badminton, but they have that ball with the little thing attached to it, the birdie. It will land ball side down because that's the heavy side. The little feathery part is light. So that usually sticks up. Same with coins. So in this particular example, since heads was 44 times, it landed tail down most times, which means the tail side of this particular coin is probably the heavier side. However, it's not a fair coin because we didn't get 50 heads up, 50 tails up. Let's try another example. Example 5, you conduct an experiment and roll a die 600 times. You roll a 6 200 times. Part 1, based on your observations, if you roll the die one time, what is the probability that you will roll a 6? It's a probability. I need my fraction. I rolled the die 600 times. So that's my denominator. The 6, which is my event, happened 200 times. So that's my numerator. This reduces to 1/3. So if we take this particular die and we roll it, the probability that we'll roll a 6 is 1/3. If a die is weighted, then there is not an equal probability of rolling any of the 6 numbers. So the question is this die weighted? And the answer is yes. It's weighted. Because we got a 6 1/3 of the time. If it was not a weighted die, then we should get a 6 1/6 of the time. Every number should show up 1/6 of the time. There used to be in casinos a big scandal with weighted die when people were playing craps. In Vegas and larger casinos, that's no longer an issue. But they used to actually weigh their die so that certain numbers would show up more often and it would give the house a better chance of winning. So anyway, this is the end of 11.4. This is just an introduction to what probabilities is. We did a few examples talking about the difference between theoretical and empirical probability. And then we looked at some of the notation that should come up. So the remaining sections that we're going to cover are going to be different types of probabilities. And these sections can get a bit long, and some of the probabilities can get a little bit complicated. So just make sure that you're keeping up and let me know if you have any questions.